webinar. And also, I must say that everyone was impressed with you, Peter, hosting the whole webinar 3 weeks ago with your car battery from your mobile. That was quite impressive, but I think everyone's happy that we postponed this. Now I'm actually in Oberwolfach, and I should thank the staff at Oberwolfach for giving me one of the Oberwolfach meeting rooms and the bandwidth for the seminar, and of course the very nice coffee from the coffee machine here. And my talk is meant more or less as a preparation for Markus' talk on the actual knots-quiver correspondence. And I will go through the basics of quiver representations and what are these Donaldson-Thomas invariants of quivers. And I will only do the simplest case, which is already very, very rich theory, the so-called Donaldson-Thomas invariants of symmetric quivers. I will tell you later why this is a very special case. And this is also quite nice as a continuation of the mini VBAC last week at Utrecht, and which was about quivers and sheaves. And now we are really back to the basics of what is a quiver representation and why does it give an interesting Donaldson-Thomas theory. All right, so the overview of the talk is first I will just introduce the category of quiver representations, thereby fixing quiver notation. And anyone is invited to compare this to the category of vector bundles on a smooth projective curve. Yeah, and you will see lots of similarities, but then you will also see the differences when we define the so-called moduli spaces of completely reducible quiver representations. Then I will show you some examples of this with classical geometric objects. Then I will introduce these DT invariants corresponding to symmetric quivers. Discuss one of the main surprises of DT theory, namely the integrality of these DT invariants, and that would actually be the main point for the knots-quivers correspondence later, and also work out some examples by hand there with some classical algebraic geometry. Okay, so that's the plan for the talk. So let me start with the definition of quiver representations, or actually the definition of quivers. Quiver is really just an oriented graph, and this is just a colorful name for an oriented graph invented by Gabriel, because he said, well, a quiver is something which you carry on your back containing arrows. That's why it's called a quiver. Yeah, it's a graph, oriented graph, so it's something containing arrows. So we fix a set of vertices Q0, and the arrows we already know by, well, like a map. It's an arrow alpha from I to J. All right, we will see examples in the following. Then we define what a representation of a quiver is. And let me just work over the complex numbers all the time for simplicity. And so for every vertex in our oriented graph, we fix a vector space Vi. And for every arrow, alpha from I to J, we fix a linear map V alpha from Vi to Vj. Yeah? So you could also say you can imagine this oriented graph as a small category with vertex being objects and arrows being morphisms, and then the representation is nothing else than a functor from the small category to vector spaces. For every vertex, you have a vector space. For every arrow, you have a map. That's it. All right. Then we need a notion of morphisms of these quiver representations. And a morphism from a representation V to a representation W means we have a bunch of linear maps phi I between all the vector spaces. Yeah, so the representation V consists of vector spaces Vi. The representation W consists of vector spaces Wi, everyone corresponding linear maps, which are compatible with these data V alpha, the datum for the maps. And this compatibility map is just a commutation relation. If I first go V alpha, then phi j, this is the same as going first phi I, then W alpha for all arrows. Okay. And finally, to make this into a category, we define composition of morphisms component-wise. What does it mean? Well, a morphism has components phi I, and these we can compose as we compose linear maps component-wise. Okay, so we have three ingredients. We have a notion of representation, we have morphisms, we have a composition of morphisms. In fact, this gives a category. In this way, representations of Q over the complex numbers form a C-linear abelian category rep CQ. And now this category is defined in a bit artificial way, but now we'll see that it's actually something we all know. Namely, it really looks like a category of modules over an algebra. This is the content of the next page. The category rep CQ, which I just defined, is equivalent to the category of modules over the so-called path algebra of the quiver. And path algebra, the notion of path algebra already tells you how to define this. I mean, think about the group algebra of a group. You know how to define it. And here you see how to define the path algebra of Q. Well, as a vector space, this algebra has a linear basis consisting of all the paths which you can go in this oriented graph. So just a composition of arrows. And the multiplication is given by concatenation of paths, if possible. And if two paths are not compatible, then you define the product as 0. Yeah? So this is, you could also say it's a semi-group ring. And in this way, you get an associative unital algebra over the complex numbers, and modules over this algebra are equivalent to representations of this category. That's one of the first things you show in the course on quiver representations. And the actual important homological property is that all higher x greater or equal to, in this category vanish. This is easily proven by just writing down standard projective resolutions for the objects. And now, of course, you see the similarity to vector bundles on algebraic curves. That's also a category with all higher x vanishing. Yeah. So, and instead of vector bundles, we now here have a source of modules over non-commutative rings for a natural category with all higher x vanishing. And that is the important similarity, or one of the important similarities. Okay. We need a little bit more, namely, here I said that all the higher x starting from 2 vanish, so there are 2 non-vanishing x, namely x0 and x1, and we need to have a formula for the dimension of x0 and x1, and for this we will now introduce the so-called Euler form of the quiver, which is really easy to read off from the quiver. So first, for the definition, for a representation V, I define its dimension vector as, well, I just take the dimension of all the vector spaces which are involved in the quiver representation, and I just treat this as a vector with non-negative integral entries. That's the so-called dimension vector of quiver representation. And I define the so-called Euler form on the free abelian group generated by the vertices, as Euler form of 2-dimension types D and E is sum over all vertices, di times ei, minus sum over all arrows, alpha from I to j, di ej. So this is in general, non-symmetric bilinear form, encoding the arrow structure of the quiver. And you see that it is in general non-symmetric, well, because, well, we take the sum over all the di ej along the arrows I and j. Yeah, so in general, this is non-symmetric. This will play an important role later. This is called the Euler form of the quiver, which is just defined in terms of the graph structure, but it is also the homological Euler form of the category of representations. That's the content of this theorem. Euler form equals homological Euler form. So this Euler form, which I defined just in terms of the oriented graph, is the same as taking dimension of hom minus dimension of x for 2 quiver representations. The important thing about this is that this difference, the dimension of hom minus the dimension of x1, does not depend on the individual isomorphism classes of the quiver representations, but it depends only on their dimension vectors. Yeah, because here this difference is, well, I just take the dimension vectors and plug them into this non-symmetric Euler form, which just means, well, like you, yeah. It's the Grothendieck, essentially the numerical Grothendieck group of this category of representations. Okay, this Euler form will play a role later. So these are the basics about the category of quiver representations. And if there are some questions, or if I should go back to the previous page, then please let me know. Otherwise, I will proceed to the more geometric aspects. And you might think about whether you have a question. I'll have a sip of coffee in the meanwhile. No questions yet, so let me continue. All right, now the geometric approach to quiver representations. I want to define kind of a moduli space encoding all the possible representations. This is much, much, much easier than with the moduli spaces of vector bundles on algebraic curves, because here I can realize the moduli space is just globally as a quotient, yeah? Whereas in the vector bundle case, I first have to consider some Hilbert and quad schemes, and then locally write something as a quotient by some SL action. Here I have a global object, and I can globally define moduli spaces just by taking a Hilbert quotient. And this we will see now. We fix a dimension vector. These are the discrete invariants in the quiver representation, the dimension of the vector spaces involved. Okay? And, well, fixing a dimension vector means fixing the vector spaces up to isomorphism, and let's just fix the vector spaces VI. So now we are only considering representations of our quiver on these fixed vector spaces VI. And I define the representation space, RD of Q, as direct sum over all arrows alpha from I to J, from VI to Vj. And sorry for the mistake, this little k here should be complex numbers because I'm working over the complex numbers all the time. Sorry for that. That's a little typo. So what is a point in here? A point in this, well, look at this as an affine space. And a point in this affine space is a tuple of linear maps parameterized by the arrows in the quiver. And this defines precisely a representation of the quiver. We already fixed the vector spaces, VI, and the other datum you need for a quiver representation is precisely these linear maps V alpha. And these V alpha constitute a single point in this representation space. Okay, and on this space, we have a very nice action of a group, GD, which is just the product of all the general linear groups of the vector spaces VI. And this action is like a graded version of the adjoint action. Yeah, look here. I mean, if you look at it from a distance without the indices, we are looking at the action G, V, G inverse. So just the classical adjoint action or conjugation action. And we make sense out of this GV inverse by putting some indices in. The G, the group elements, are indexed by the vertices of the quiver, and the V, the maps, are indexed by the arrows of the quiver. And if you keep this in mind, then this is the only reasonable definition which you have. Okay, so now we have a very nice reductive linear algebraic group, product of GLs, acting on a very nice affine space. This action is in fact linear because it is somehow of adjoint type. And what could be better than that? The main observation is that the orbits correspond bijectively to the isomorphism classes of representations. And this is the one point we have to understand. And for this, let me quickly go back to one of the first pages where I defined the notion of morphisms of quiver representations, and then go back to this. So just keep this in mind. This is the action. And for this action, we consider the orbits, and they should be isomorphism classes. So now we'll go back a few slides. Here we go. That was the notion of map between quiver representations. And now look, if these phi's are invertible, then you can get the W as phi j V alpha phi I inverse. Phi j V alpha phi I inverse equals WA. That's precisely this adjoint type action. And so here you see that if these linear maps here are invertible, then one representation is produced out of the other by this adjoint type action. So let me go back to this. So that's the proof of this observation that the orbits for this group action correspond bijectively to isomorphism classes. So that motivates, if we want to have a moduli space, then we better take the space and mod out this group action. But of course, we know that geometric invariant theory doesn't work like that. In general, we do not get a quotient parameterizing the individual orbits, but we only get a quotient, the classical Hilbert quotient, spec of the invariant ring, parameterizing closed orbits. So now we have to find out what are the closed orbits for this action. Next page. Okay, so as I said, I will just define the invariant theory quotient, just the spec of the invariant ring, RD of Q, double quotient by GD, and this parameterizes, we know from the very beginning, the closed orbits. It parameterizes the closed orbits of GD and RD. The orbits correspond to representations, to isomorphism classes of representations. So now you only have to know to which representations do the closed orbits correspond, and they correspond to the completely reducible representations. So a representation which is a direct sum of irreducible representations. Irreducible representation in the very strong sense, it has no sub-representation except 0 and itself. Yeah. Just a quick side remark, the usual terminology in quiver representation theory for an irreducible representation is simple representation. I will not use this notion of simple representation because I know of the analogy to vector bundle theory, and in vector bundle theory, a simple vector bundle is something not the same as an irreducible vector bundle. Simple means trivial endomorphism ring. So this is not what I mean here. I really mean irreducible in the strong representation theoretic sense. There's no sub-representations at all. Yeah. Okay. End of side remark. So we have a moduli space for completely reducible representations, which is an irreducible normal affine variety. Let's just quickly see why this is true. It is an affine variety because I define it as the spec of a ring of invariants, which is finitely generated by Hilbert. It is normal because, well, it's the spec of an invariant ring inside just a polynomial ring. So it's definitely normal, and irreducible just because RD of Q is irreducible. The irreducible normal affine variety, and generically, I know the dimension of the space. Namely, the dimension is usually 1 minus Euler form dd in the case that there exists an irreducible representation of this dimension vector d. I will not discuss this condition of existence of an irreducible representation, but let me just say there is a purely numerical criterion in terms of the dimension type and in terms of the structure of the graph structure of the quiver, which tells you whether you have an irreducible representation or not. So this is effectively decidable by a one-line calculation. Yeah. So this is not an abstract thing that you don't know whether there is an irreducible or not. There is a very nice criterion due to Le Brun and Procesi giving you a numerical criterion for this existence of an irreducible representation. So in this case, we know the dimension of this variety. And the interesting thing about this dimension formula is you see that the dimension, because this is a quadratic form, the dimension depends quadratically on D. So in particular, if you replace D by a multiple of D, then this dimension will grow quadratically. So that's a pretty strong condition. So these are fast-growing, typically fast-growing in dimension, these moduli spaces. Okay. So, and before I come to examples, which somehow give you a bit of a feeling for these moduli spaces, let me just make one remark. Usually, if you hear about moduli spaces of quiver representations, people will talk about a stability and moduli spaces of stable representations. I'm not talking about this here. I'm talking basically about zero stability. But let me just make a remark. If the quiver has no oriented cycles in it, then the moduli spaces I'm defining here always reduce to a single point, which might look a bit boring, yeah? And the reason is that in this case, if the quiver has no oriented cycles, then there is a dilation action on the vector space, which is compatible with this adjoint action. And so the only closed orbit is the vertex, the zero representation. This is the case if Q has no oriented cycles. But this is definitely not the case I'm interested in for the purposes of this talk and for the purposes of Markus' talk later. And that's why I'm not working with stability. Yeah? I mean, to remedy this, you usually introduce a notion of stability of quiver representations. And then, even if the quiver has no oriented cycles, you get more interesting moduli spaces. So then you replace this construction, taking the spec of the invariant ring, by the more general, take the approach of ring of semi-invariants for a certain character of the group. But that's not what we're doing today. We're just taking these very first type of moduli spaces. So that's the final sentence here. For the purposes of these Donaldson-Thomas invariants, which I will introduce in due time, Q will always be assumed symmetric, which means if you have an error in one direction, you have an error in the other direction. And that means the quivers I will consider almost always have lots and lots of oriented cycles. So even these moduli spaces will be very interesting. We will come to these moduli spaces now. Finally, I promised this several times on the next slide. Here we go. Some small dimensional examples. So let's first look at the quiver, which is a single vertex and a single loop attached to it. So this loop should really be attached to this vertex, but it's just my poor LaTeX abilities which prevented me from drawing this correctly. Let's work out what are the representation variety and the action in this case. The representation variety is just the space of D by D matrices. Yeah, because here at this vertex, you put a d-dimensional vector space, and this arrow is represented by a map from this d-dimensional vector space to itself. So the space is just an endomorphism, and you have an action of GLD, and it's just the usual adjoint action. Yeah. I mean, I promise this is kind of a graded version or graph graded version of the adjoint action. And here it is the honest adjoint action. And then we know for the adjoint action, the quotient by the adjoint action by Chevalier's theorem is just affine space. Or explicitly, to a matrix, you attach the coefficients of its characteristic polynomial. These are all invariants for the adjoint action, and that gives you an isomorphism between this and affine space. So that's our first quiver moduli space, affine space. Next, let's look at pairs of matrices. So let's take a single vertex and two loops, two loop quivers, and then what you're looking at is simultaneous conjugation of pairs of matrices, for which these quotients are already very, very complex. Just let me give you one not so complex example, because I will later use it in DT theory. Two-dimensional representations. The two-dimensional representations are an affine 5 space. And this is not so difficult to see. This you can really do as an exercise in linear algebra. So representation of this quiver is, of this dimension vector, is pairs of 2 by 2 matrices, which you consider up to simultaneous conjugation. And then there are 5 invariants under conjugation, namely the trace of the first matrix, the determinant of the first matrix, trace of the second matrix, determinant of the second matrix, and then you need a 5th invariant, which is the trace of the product of the 2 matrices. And then you can see there's a very nice linear algebra exercise that these 5 invariants are indeed algebraically independent and determine the closed orbit. So you have an A5 as moduli space. This is one of the few moduli spaces for this quiver which can actually be computed in coordinates. All right, third example is, well, okay, now we have 2 vertices in the quiver, and we have a certain number of arrows in this direction, and it's two arrows in this direction and 2 arrows in the other direction, and we consider very modestly the dimension vector 1, 1. Then our moduli space is 4 tuples A, B, C, D, such that AD equals BC. So just the cone over the Segre embedding of P1 cos P1 in P3, or just the standard quadric in A4. And this is an example which we also will go back to later. And finally, generalizing this, let me consider, this is now the most complicated example which we will later treat with the DT theory. 2 vertices, m arrows in one direction, m arrows in the other direction, and the dimension vector is 1k. And then if you work through the definition, then you will see that the moduli space is the space of m by m matrices of rank less than or equal k. Sorry, okay. And there's a very interesting variety, a determinantal variety, with affine, irreducible, normal, but it is, of course, in general singular, and that's very interesting that, I mean, already in this example, you had a singular variety, because here, well, as I said, this is the cone over a Segre embedding, and the vertex of the cone is, of course, a singularity. Here you have really non-trivial singularities, and these will then finally be interesting for DT theory. So that's somewhat typical small moduli spaces, which you can get as quiver moduli spaces. There are many more examples which you can compute by hand, some more examples which you can compute by hand, but the resulting varieties usually don't have a name. I mean, these examples here are all varieties which have a name: affine space, determinantal variety, cone over the Segre embedding. But in general, if you do this computation for arbitrary quivers and dimension vectors, computations will become very hard, and the resulting varieties will be nothing you have ever seen in any other field of algebraic geometry. All right, so this is some small dimensional examples, but that's enough for the purposes of the following. Okay, so that was the second part of the talk. So now we have seen, or the third part even, we have seen the category of quiver representations, which is modules over a certain algebra, which has a special homological property of all higher x vanishing. Then we have seen that we have a global construction of a quotient. We just take a whole global parameter space and we just take an invariant theoretic quotient giving us a moduli space. And we have seen that in small examples, we can work out these moduli spaces well because we're essentially only doing linear algebra. We're just looking at tuples of linear maps under change of basis. All right, and now we come to the much more non-trivial and more difficult to motivate Donaldson-Thomas theory. So now things will involve some more complicated formulas, which I will try to explain in a bit more detail and motivate a bit. But there might be some details in the following formulas, in particular the signs, which are very difficult to grasp when you see this for the first time. Okay, let's see. So this is a definition due to Kontsevich and Solberman. And from around 2010, this is the motivic Donaldson-Thomas invariance. So what they, before giving you the definition, let me very briefly say what they try to do. So I will give the definition of motivic Donaldson-Thomas invariance only in the case of the quiver. That is kind of a toy example. What you really want to have is motivic DT invariance for 3 Calabi-Yau varieties. And this you want to have as a mathematical precision of the notion of BPS states in string theory. Yeah. So in string theory, you're looking at strings vibrating inside a 3 Calabi-Yau, and you want to understand the associated physicists want to understand the associated quantum field theory, which is really difficult and not mathematically well defined. But what is clear is that there are some lowest energy states, lowest energy vacuum states, the so-called BPS states. And the BPS states admit a mathematical model, which is this Donaldson-Thomas theory, which was first formulated by Kontsevich and Solberman in the 3 Calabi-Yau setting. And we're, as a toy example of that, we're looking at local curves in the non-commutative world, which is quivers. All right. So from now on, we have to assume that the quiver is symmetric, because otherwise the DT invariants can still be defined, but they have completely bad properties. Yeah. So quiver has to be symmetric, which by definition means the Euler form is symmetric. And the Euler form being symmetric means that for any two vertices I and j, the number of arrows from I to j is the same as the number of arrows from j to I. That's the symmetry assumption. Let me quickly go back to the example page. All these quivers which I wrote down here are symmetric, because here I had 2 arrows in one direction, 2 arrows in the other direction. Here, m arrows in one, m arrows in the other. And here, well, this is just the loops, and there's obviously also symmetric. So all these examples were already symmetric. So that's the assumption I have to make. Otherwise, the DT invariants are just plainly bad. We look at a certain formal power series. And this is a formal power series in as many variables as we have vertices in the quiver. And the coefficients of this power series are rational functions in q to 1/2. Okay? And so here is a series, PQ of QX, that's usually called the motivic generating series of the quiver, for reasons which I will explain in a few minutes. So look at the structure of the series. So it's a sum over all dimension types, and then I have x to the d. So that means that it's just a monomial in the various x variables. Yeah, so I have an x variable, xi, for each vertex in the quiver, and this is just a monomial x to the d. And the coefficient of this monomial is minus q to 1/2 Euler form dd divided by a product of 1 minus q1, q inverse, up to 1 minus q minus di. If you are into formal power series, you might recognize this as a q hypergeometric series. Yeah? So this is a q hypergeometric series because the denominator here is a product of so-called q factorials or q Pochhammer symbols, and the numerator is the variable q to a certain quadratic form. And the properties of this quadratic form make for the various different properties of this formal series. So this is something known in many branches of mathematics, a q hypergeometric series. Okay, that's the starting point. Now we'll explain in a few minutes what it has to do with the quiver, except for this for this quadratic form of the quiver appearing. And now what Conservation and Solbermann suggest is you take this formal power series and you factor it into an infinite product. Factor this series into a product, and I write exclamation mark as, well, we first have to see that it is possible to factor it into a product, and the reason for this is that it has constant term 1. Think about it, whenever you have a formal power series with constant term 1, you can factor it into an infinite product of terms 1 minus x to the d. Okay, and now this is the line which is very difficult to motivate. Let me just let's look at this complicated thing from a distance. So we have a series which we should assume as being natural because it's of Q hypergeometric type. And then the idea of Conservation and Solbermann is factor it into a product. This is possible. And the terms in this product are of the form 1 minus some power of Q, some power of X, basically. Yeah, and you can easily see if you have a series with constant term 1, then such a factorization exists. Now, things are made complicated by several different things. Well, first of all, we're always working with half powers of Q. There are some reasons in Donaldson-Thomas theory for doing this. And this is why you always have half powers of the Q here. Second ingredient is that you always have an additional product K, which wouldn't be strictly necessary, but it's just there, but not in the exponent. And then in the exponent, you're putting an extra sign. And this sign might look random, but this sign is somehow an essential feature of Donaldson-Thomas theory. Without this sign, you don't get interesting invariants. Okay, so yeah, this is difficult to grasp, but let's just, well, in a nutshell, we have a Q hypergeometric series. We brute force factor it into an infinite product. And in this infinite product, we have certain exponents appearing. And these exponents we collect in polynomials. Namely, we collect all the CDI, these exponents here, in a polynomial in the variable yeah, we collect it along the index I here. Again, as kind of a Poincaré polynomial, but not in the variable q to the I, but minus q1 half to the I. And then we also have a complicated factor in front. So it would be, pedagogically, it would be a very good idea to first get rid of all the signs and all the half powers, write down this, and then somehow decorate everything with enough signs and half powers for the honest thing. Yeah, so it's, I know that this is quite complicated, but that's the way you have to define it. Otherwise, you don't have any of the nice theorems, which I will now show you on the next slides. Yeah, so that's how you define motivic Donaldson-Thomas invariants, and that's unfortunately the easiest definition you can have. Okay. Yeah, so now after defining this, well, out of my Q hypergeometric series, I get a bunch of, well, what do I get? I get a bunch of formal power series in Q2 plus, well, formal Laurent series in Q to the plus minus 1/2, depending on the quiver and a dimension vector D. And now these are called the Donaldson-Thomas invariants, and by some magic, Conservation and Solbermann say this is the correct definition of BPS state counts in string theory. And we are only interested in the mathematical properties of these DT. And that comes now on the next page. Yeah, 10 minutes to go. That's quite nice. We first do examples. Okay. Yeah, let's first do an example, which is maybe a good idea because the definition is so complicated. Now I will work out everything just for this quiver, which is a single vertex and a single loop. I cannot put both screens in comparison, so you have to trust me that the motivic generating series in this case is just this. Aha, this looks much more reasonable than this general stuff on the previous slide. So for this simple quiver, which is just a single vertex and a single loop, the series we're looking at is sum over all d, x to the d, divided by some q analog of the factorial, or q Pochhammer symbol. Okay. And now there's something in combinatorial theory, basically, because you usually prove it using partitions, called the Q binomial theorem, which tells you that this sum is equal to the product over all k of 1 minus q to the k plus 1x. So this is a very simple example where you can have such a Q hypergeometric series, and you can easily factor it into a very nice infinite product. It's a fun exercise to give a proof of this theorem using, well, using just expansion of the product and then counting partitions with certain statistics. And this gives us the fact that that for this quiver, the dt invariant dt1 is just Q, and all higher dt invariants are 0. I have to skip the details here because now you have to really match this to the complicated definition on the previous slide. But well, at the moment you can just believe me that this is a very simple case. dt1 is just Q and all other dt invariants are 0. So that's a very simple example of what happens here. Okay, and in fact, there are only 2 more quivers for which an explicit product factorization of this P series exists, and where it is really explicit. And this one example is the quiver which is just a vertex and no arrows at all, and the example where you have 2 vertices and 1 arrow in each direction. So these are the 3 connected quivers for which you can do this infinite product thing by hand, and where you know all the dt invariants by hand. And in all other cases, the dt invariants are not known in a closed formula. Yeah, so this is really something very, very non-trivial. Okay, observation. And this is the true nature of this P series. As I already told you, this is usually called the motivic generating series of the quiver. If you look at this final formula here, this P series, if instead of the variable Q, which I used, you plug in the Lefschetz motive, then what you get is the series sum over all D, virtual motive of the representation variety, divided by virtual motive of the group times formal monomial x to the d. And now I have to explain what I mean by virtual motive. Well, motive for me means very naive motive. I consider classes in the Grothendieck ring of varieties, and I localize this Grothendieck ring of varieties at plus minus the square root of the Lefschetz motive, and I localize at all the terms 1 minus L to the I inverse. Of course, it's clear that this is a very dangerous thing to do and that we are losing lots and lots of information, because in the Grothendieck ring of varieties, we know that the Lefschetz motive is actually a zero divisor. And now we are localizing at this zero divisor, meaning we are implicitly taking a huge quotient. So we are losing lots and lots of interesting information about about motives. But we know, because there are some motivic invariants which factor over this localization, we know that some information is preserved, like what is it, the virtual Hodge polynomial, for example, exists on this level of localized representation varieties. So this is not the zero ring we are talking about. This is good to know, yeah? Okay, so this is a dangerous localization, localizing at a zero divisor, the Lefschetz motive, but there's still something to observe here. And then we define the virtual motive of a connected variety as the motive of the variety, and then we shift it by minus half power of Lefschetz motive to minus dimension of x. So that's it has to do with virtual fundamental classes in appearing in motivic Donaldson-Thomas theory. For us, it's just a standard convention for DT theory. That's why we have to work with these half powers of the Lefschetz motive. And let's just believe for a moment that's the right thing to do from the DT perspective. And then what we're doing is we're considering the motivic generating series. So we're taking the virtual motive of the representation space, divided by the virtual motive of the group which acts. Or you could also say we're taking the virtual motive of the quotient stack of representations modulo the group. Yeah, so this is really the generating series of motives, virtual motives of quotient stacks. This is this P. Okay, and we're taking this motivic generating series and factor it into a product, and then we hope that in this product magically some interesting invariants called DT appear. And the justification is just on the next page, the main theorem. So first of all, the first justification was Efimov's theorem from 2012 that these DT invariants, which I defined as formal series with rational coefficients in half powers of Q, are actually polynomials in Q with non-negative coefficients. And this is really, really surprising. I will shortly go back to the definition on the other slides, and then you can really appreciate this theorem. So take this theorem, we get a polynomial with non-negative coefficients. Let's go back to the definition. Okay, so here that was the definition in this line. The dt was formally just rational coefficients and then just a formal series in positive or negative half powers of q, because we are collecting all these mysterious exponents in this triple infinite product. Yeah, so it's absolutely not clear that the resulting thing is a polynomial, and that's one of the magics. In fact, that's what Kutsevich and Solberman conjectured from the very beginning, and that was then confirmed by Efimov. And then if you have such a result, then of course the question is, well, what is this? Yeah, I mean, whenever you have a polynomial with non-negative coefficients, you want this polynomial to be a Poincare polynomial of something. Yeah, you want some manifestly positive interpretation of this, and there are many of them. So and now this is a slide ad for a paper, for an overview paper which I wrote last October about several geometric, algebraic, and combinatorial interpretations of the T invariants. And in the years since 2012, well, around 10 different such interpretations were developed, which is very interesting. And these interpretations are of very different nature. Some are purely combinatorial, counting so-called break devices in certain graphs. Some are algebraic, where these non-negative integers appear as, well, these polynomials appear as Poincare-Hilbert series of some graded vector spaces defined algebraically. And some interpretations are geometric, where this polynomial is just a Poincare polynomial in some cohomology theory. And there are about 10 different of these, and there's a survey paper on this, which you can find here if you want to see more of that. I will now just pick one of these interpretations, namely a theorem which I first developed together with Sven Meinhardt, and there were some gaps in there, and these were closed by Meinhardt, and there was an alternative alternative proof by Ben Davison and Sven Meinhardt. This DT invariant here is the Poincare polynomial in intersection homology of these moduli spaces, which we saw. Yeah. So there's a typo here. I called this S-sim for semi-simple. So that is the moduli spaces, which I introduced a few minutes ago. And then these are usually singular varieties. And I take the compactly supported intersection homology of these singular varieties. And the resulting Poincare polynomial is indeed this dt. And if you look at this, here I'm still taking these half powers in the Poincare polynomial, but we know from Efimov that only full powers of Q appear. So in particular, implicitly in here is a purity theorem that all odd intersection homology is actually zero. Yeah, so there are many very special purity properties even for this. And this formula is true in case there is an irreduced representation, and otherwise the DT invariant is zero. And now I'm almost out of time. Maybe I have 2 more minutes because we started at...
Yes.
Yeah, okay. Just let me just illustrate this with 1 or 2 examples. No, let me give you the full picture. Okay. This is a page with examples, so let's just look at the second example, because I think this is quite illuminating. I showed you this example of this quiver with m arrows in one and m arrows in the other direction at this dimension vector. And the moduli space was matrices of rank less than or equal k, such a determinantal variety. And it is known and easy to see that this variety admits a small desingularization by a variety which is just m copies of the tautological subbundle of the Grassmannian. So very classical geometry, yeah? So you take m copies of the tautological subbundle on the Grassmannian GRKM, and this defines a small desingularization of this determinantal variety. And then from standard cohomology of the Grassmannian, you can work out what is the intersection cohomology of the moduli space, is the cohomology of the Grassmannian shifted by a certain degree. And so in this case, you can compute the DT invariant from algebraic geometry. And there are some more examples where you can do something like this. And so this gives you a nice interplay between the DT theory, which is just elementary but very hard definition, factor a hypergeometric series, and algebraic geometry, where you actually deal with intersection homology of certain nice affine singular varieties. And thank you very much for your attention. That's it. Thank you.
Thank you very much, Markus, for this nice talk. So are there any questions or comments?
No.
Please just unmute yourself and speak up if you want to ask something.
Yeah, just one question. Those last examples are in your paper, or there is some reference?
Yes, in the survey paper, there all these examples are worked out in detail. Yeah.
Okay, they're very nice. Very nice talk.
Thank you very much. Yeah. Yeah, I mean, there are not so many examples which you can really work out by hand and which are related to some unknown varieties, but this is one of the nicer examples with this determinantal variety, and there are a few more, and these are essentially all worked out in this paper.
Yeah, it's very nice, that one, the second one.
Yeah, that's really
the Grassmannian, yeah, it's surprising.
I didn't discuss this final example where you have the M loop quiver. Yeah? So this is a single vertex and M loop attached, and then you get the value of the T polynomial at 1 is this very complicated Möbius inversion. So you see 1 over d squared, and then you do a Möbius inversion over certain signed binomial coefficients. And this is quite surprising. This is something which you get from one of the combinatorial interpretations. And it means, well, the left-hand side by this geometric interpretation is not combinatorial, but it's intersection Euler characteristic. Yeah, so this is the intersection Euler characteristic of certain variety is given by this Möbius inversion over signed binomial coefficients. And this is something which you can, I think, never obtain in any geometric way. Yeah, so you might really have an interesting interplay, taking all these 10 different interpretations of DT invariants and jumping between algebra, geometry, and combinatorics back and forth. And this, that's a quite fun game to play for some time.
Yeah. Also, the previous one that you used the powers of that tautological bundle is right. That. Yeah. Impressive.
Could you say something about how difficult could it be to define all of this for quivers without oriented cycles?
Yes, I can tell you a little bit about it. Then, of course, you have to work with some stability, because otherwise the moduli spaces are trivial. But then what you do is, okay, so the starting point for the definition of DT was this motivic generating series.
Mm-hmm.
And then you take the motivic generating series again for the quotient stack, but not of all representations, but just of the semi-stable representations. Yeah, so here you write down RGQ, but only the semi-stable locus. And then you can formally do the same definition of DT invariance. And the theorem of Meinhardt and Davison and myself still holds. Then you take here the moduli space of stable, semi-stable representations, and this is still true. Yeah. And then again, if you know how to compute these moduli spaces, then you can really work out, well, these are singular, and then if you know how to compute intersection homology, then you can really compute DT invariance. So it more or less literally translates to the same case.
You say, when you say semi-stable, you mean so the semi-invariance will affect to a character, right?
Exactly. Yeah.
Okay. Thank you.
You're welcome.
There's a question here in the chat. Is there a direct intuition to what DT looks like when we have a quotient of the path algebra to some relations? Yeah, so I guess,
I think, well, you definitely need some good homological. I mean, then you're looking at path algebra, modulus, and relations, and the category representation of it. You definitely need some very good homological properties. Yeah. So I mean, here it's just you have global dimension 1, or you might have 2 Calabi-Yau or 3 Calabi-Yau. And I mean, the interesting situation usually is 3 Calabi-Yau. So you first have to know whether your relations in the quiver give you a 3 Calabi-Yau quotient. This is usually known if the relations are the Jacobian relations for some superpotential on the quiver. But then in this case, you don't just take the moduli space, but well, you have to refine everything, because well, then you're considering motivic vanishing cycles, and well, it's the full 3 Calabi-Yau picture, which is much more complicated. But you definitely you can't just say I take just some relations on the quiver, because every finite dimension algebra is essentially path algebra of a quiver modular relations. Yeah, I mean, every algebra is Morita equivalent of an algebraically closed field to path algebra of a quiver modulo certain relations. So if you just say, I want to do this for quiver with relations, that means I want to do DT theory for all modules over all algebras at the same time. This certainly can't work. DT theory needs some very good homological properties, typically 2 or 3 Calabi-Yau. But in this special situation, then of course you can do this, and that's the complete Kontsevich-Solverman story of motivic DT invariants for 3 Calabi-Yau situations, which is quite different from this quiver situation. Sorry for the negative answer. It's just a completely different story. Yeah.